Okay, so welcome back to another video. Here's a different kind of problem that I think it might be interesting to share. So let's first actually go a little bit of a definition. So first, the definition of an nth iteration of a function for f of x is written as f sub n of x equals the composition of n many times f. So I forgot to put that down. So this actually can go to n times, and such that n is a positive integer. Now, with that definition in hand, the question we would like to figure out is what is the derivative of that nth iterated function where f of x is equal to e to the power x. So if, in other words, an example, please do not, just also not to get this confused, we're not asking for what is the nth derivative of this iteration. We're looking for what is the derivative of some nth iterated function. So for example, what is the derivative of just f of x itself? So f1 of x, that's just e to the power x. Or what's the derivative of f composed 2, so f composed x twice, so f of x, in other words, what's the derivative of e to the power x, you know, so on and so forth in that example. So as you can see with this sort of composition, this actually forms a little bit like a titration of some finite height, in other words. So to put this simply, as we can see, I think we know that as we come along with some general pattern to see like what's the closed form for this, you know, iterated formula, specifically for this function, you can see that in order to show that, we would actually have to use some sort of mathematical induction, and that's actually the steps we're actually going to take forward from that. But to start off small, we actually of course, in order to find that closed form, we want to do things one at a time and take a look at the patterns to see like what kind of observation speculation can we make to make that sort of generalization of that closed form. And then from there, in order to show that it works for every single time, for every step, then of course that's where the mathematical induction, you know, strategy comes in. So anyways, let's actually just get into some examples and then we'll actually get into the deduction. So for the n equals 1 case, so let's actually just plug this back in. So in other words, that's the same thing as saying f of x. Then that means we have to see that the derivative of f of x, or in other words, the derivative of e to the power x is basically just e to the power x. And in other words, we can actually generalize this in a little closed form of a product series. And we can write that as the upper index is 1, and then our starting index is 1 for k is equal to 1 of f sub k of x. All right, so let's actually move on to, you know, step number 2. So n is equal to 2. That means the derivative of f sub 2 of x, so composed of that, that would actually mean that we have to plug e to the power x back into this form over here. So that means we have the derivative of e to the power x. So in other words, if we just apply the chain rule and all that, so we would have that this is just e to the power x, and then multiplied by e to the power x. And if we actually write this further, then we can put that as a little product series from k is equal to 1 and then all the way up to 2 of f sub k of x. So let's actually try, let's go for n is equal to 3. So n is equal to 3. So that means the derivative of f composed 3 times of f of x, which is equal to 3, or the derivative, and then just plug this back in. So that means we have a towers of e's going 3 times, so e to the power e, and then to the power x. Then as you see that we actually just again apply that same theory, that same rule for chain rule. So it's e to the power x multiplied by e to the power x, and then multiplied by e to the power x. In other words, can write that as the product series going from k is equal to 1 to 3 of f of k and then x. Okay, so at least we're getting somewhere. So if we play around this so and so forth, then we can actually come to that generalization for the nth iterated formula for the function of f of x, or for e to the power x. And we can see that after doing also, we would get that the derivative of f sub n of x is going to equal to the following product series going from k is equal to 1 of n of f sub k and then to the power x. Now, a lot of you might be thinking that that's kind of just where it ends for, you know, of course, with the condition for positive integers n, and that's where we can say that. But let's actually show that this works for every single step at a time. So increments by 1, even stuff higher than n. So of course, with induction, we know that we have to prove things with base case, which already given that we already showed right here. So that's actually done and out of the way. Now, the second thing we have to do, or Rather, well, yes, the second thing is we have to show that for n is equal m, we have to consider that is true for some positive integer m. So we actually have to show that the m plus 1 or n is equal m plus 1 is true. And that means that everything going up forward is going to hold true for every single time you do these, calculations. So let's actually start with that induction. And I'm going to put this as we say that base case n is equal 1. That's already checked off, so that's good. So now the next is we want to assume m is equal n it holds true for m is a positive integer. I just denote a plus besides the integer symbol, denoting positive integers. And so now we have to now show that now if that's the case, so that would have to mean that then the derivative of f to the power or f of m composed of x, or the n-iterated of x, sorry about that, then we can see that it's just basically just the same thing over here, but it's replaced that m and then k is equal 1 of f sub k of x. Okay, so with this true, now show n equals m plus 1 holds true. And if we can do that, then that means that we've shown that by mathematical induction, we have found our closed formula over here that I'll box once we get to that. So if that's the case, so now let's actually get right to it. So if we see that the derivative of f to the n plus 1 iterated of x is going to equal, in other words, if we think about this in the terms of the definition of the composition, so that means I could do this for f of composed m. So I'll write it as f compose and then f and then m of x. Then I gotta write then we're taking the derivative too, so I have to put that down too. That's the main important thing. F compose f and then m. And so from here, as we can see that after taking all this, derivative with e to the power x, we can see that this actually just jumps to one and then to the other. You can see that it's kind of like stacking up again. It's like a titration, in other words. So we can actually put this little substitution and say that this can be written as the derivative of e to the power f composed m of x. And so from here, taking this derivative, again, it's applying the chain rule. So in other words, this is basically just take this out front and then take the derivative of our exponent. So e to the power f composed m of x, then multiply by the derivative of f of composed m of x. And so we just shown that if we assume that for m is equal to n is true, it's this product series, so we can actually make that little substitution over here. So just like that, we have the product series from m, or k is equal to 1 to m of f sub k of x. And so from here, now again, if we take a look at this pattern, just like what we did over here, this is actually in increments of 1, plus 1 of each time we stack this up. So in other words, if we look at it as, in other words, for e to the power f composed m of x, this is actually just increments by 1. So we can actually write this as the composed of f of m plus 1 and then x, then multiply with this product series back over here, k is equal 1 of f k and then x. But then in other words, since this is just an entire product, this is already evaluated at m plus 1 term, we could actually just put this back into the product series and just change this upper index so that the upper index ends at m plus 1 and then k is equal to 1 of f of k, and then when I write m, that's supposed to be an x. And so just like that, we actually just showed that this works for the left-hand side is indeed equal to the right-hand side. So just this and then this, and then we're pretty much done. We just did everything for the induction. We showed that the base case works. If we assume that m is equal to n is true, it holds true for some positive integer m, then that means we not only did we show that m plus 1 is true as well, then that means we actually found our little general formula for finding the derivative of the nth iterated function where f of x is equal to e to the power x for some positive integer n. And just like that, this is our little closed form for finding the, as I said it again, I'll say it one more time, this is our closed formula for finding the derivative of the nth iteration function for f of x equals e to the power x for some positive integer n. So there we have it. So yeah, that's pretty cool if you ask me.